All right, good afternoon. I'm Tom Johnson. I'm Vice President of Engineering at AGI, and today we'll be talking about how to detect, characterize, and recover from maneuvers. So as you start to do the orbit determination process, whether it's cooperative or uncooperative, you always have to deal with the fact that you have to process across maneuvers. Orbit determination is fundamental to effective space situational awareness, and so having an accurate OD solution is sort of a baseline problem or capability that you need to have for SSA. What we've done in our experience and have found to be most effective is to use a extended Kalman filter or optimal sequential filter to do the orbit determination, because that allows us to handle the maneuver problem much more effectively. And as a result, then we can use that maneuver information as a tip-off for indications of what a particular spacecraft may be trying to do. So we're going to take a look at this problem in more detail and talk about some of the technologies and approaches for how to handle the maneuver processing or maneuver estimation problem. Okay. So as we look at doing the orbit determination problem, we have to look for a couple of key capabilities that make this much more tractable and much more effective. The ability to process multiple spacecraft simultaneously becomes very useful when working with closely spaced objects that might be doing proximity operations. The ability to process real-world or relative measurements, so particularly one spacecraft that might be observing or tracking another spacecraft. And another thing that's critical is having a realistic covariance. Every estimator will produce a covariance. The question is whether you believe it or not. With an extended Kalman filter, what we're folding into the covariance problem is not just the uncertainty from the measurements, but also the uncertainty from the force models themselves. The net result of that is you actually get a realistic covariance, and that covariance now becomes a strong analytical tool for assessing what's going on and helping you to estimate your maneuvers, perform your odds association, and other related SSA activities. You can also get the relative covariances, especially when you're looking at closely spaced objects. What may not be important is the actual absolute orbits, but what's much more important is the actual relative positioning and how accurately you know that, particularly if you're trying to do rendezvous to, say, do a servicing mission, to refuel, to rendezvous with a piece of space junk, or some of the other activities that people are now concerned about. We also want to be able to fuse all measurements together into one common OD solution. We don't want to have a situation where we've got only one tool that can do this set of measurements, another tool can do another set of measurements. You need to bring everything together and take advantage of all the information that's available. We also want to make sure that we're not making assumptions about our models or about how the spacecraft operate that are no longer consistent with our experience. So for instance, it's convenient to think of a spacecraft area as a sphere, or to think that the thrust is going to be constant, or that the density model is going to be perfect. And it turns out these are reasonable first-order assumptions, but they start to fall apart in the presence of real-world data and real-world situations. And so we find that these things are time-varying, and we need to make sure that our estimators can account for the time-varying and dynamic nature of these processes. This is particularly true when we start talking about maneuvers. So typically when you have a spacecraft on orbit and it's being perturbed by the normal natural forces, gravity, Earth, solar radiation pressure, sun and lunar gravity. These are sort of the typical models that everybody puts in. But if you don't, you have to deal with the fact that many of the spacecraft are doing maneuvers. For it might be typical routine station keeping. You might be trying to stay in a longitude box. If you're a GEO, you might be trying to maintain a sun-synchronous orbit if you're a LEO. And these maneuvers are a normal fact of life for your spacecraft. But if you're trying to do SSA and estimate the orbit of that spacecraft, unfortunately, the maneuvers are typically what we call non-cooperative. The operator is not telling you what the maneuvers are, and therefore your OD process has to detect them and actually process through them without the advantage of knowing and being told in advance the details of the maneuver. So the process of dealing with that is what we call maneuver processing, which really involves several steps. You have to detect that there is a maneuver or potentially a maneuver, because sometimes you're not sure. You want to start to characterize the maneuver, so you can start to get some first level assumptions or understanding of what's going on. And then we need to recover the maneuver, and essentially we're trying to reconstruct as much as we can about that maneuver. And this gives us, again, leads all to having effective SSA. If we don't deal with this in a timely manner, or we do it inaccurately, then that just ripples into my downstream products that I'm trying to generate. I can't do effective conjunction analysis. I can't do an effective threat analysis. I may actually just lose track of the spacecraft completely, and losing track custody is a huge issue, and especially if it's an adversary satellite. We always want to maintain situational awareness as to where that is and what it's potentially doing. So maneuver detection is really the first step in understanding, is a spacecraft trying to initiate rendezvous operations or even just align my orbital planes? Is it trying to initiate proximity operations? As we look at the maneuver processing problem, again, we break it up into cooperative and uncooperative. For an SSA standpoint, it's typically all uncooperative unless you have some relationships with owner-operators where they're actually going to send you and share that information. What we can do, however, is typically we can constrain the assumptions so that we can make the problem a little more tractable and start to figure out things even in the absence of information from the operators. So we'll just define a few terms. Let's talk about maneuver detection. How do I know if I'm detecting that a maneuver is occurring? What are my criteria? What are the concerns that I have about trying to detect a maneuver? So for instance, I may have something that looks like a maneuver, but it may also be a bad sensor that's giving me measurements that are just invalid, and I can't use them to make that try to process that data. I may also have a problem where the information or the measurements may be actually for a different satellite altogether. I have an OBS association or a mistag problem. So our process has to be robust to dealing with these situations because this is what's going to happen in the real world. It's very nice to prove things out with simulated data, which is all nice and perfect and doesn't have these issues, but in the real world, this is exactly what you see. So there's no such thing as the perfect tool, but we've identified a number of best practices that we've folded into our processing, and we'll share some of that with you. Okay, so the first step, let's take a look at some sample data. So this is a plot of some measurement residuals. What we've actually done is we've taken the measurement residual from our orbit estimation process, and in our case, we've normalized it by dividing the residual by its uncertainty or its sigma. What that does is essentially gives us a normalized ratio, which in a perfect world should be within plus or minus 3 sigma. And we can see that in the graph that we're seeing here. We've got sort of editing lines at plus or minus 3. And then we can see the residual ratios from a variety of different sensors showing up in here. So the question is, if I take a look at the outlier points on the top left, where we can see we've got 2 points above plus or minus 3, those are points that are currently being kicked out and rejected by our estimator. The question is why? Is that a sign of a maneuver or not? If I have a large enough maneuver, what's going to happen is the orbit that my spacecraft is on is going to diverge from the orbit that my estimator thinks it's on, and that'll show up as large residual ratios. Now in this case, based on our experience, we can pretty much look at this and say, we don't think this is a maneuver. The reason we say that is because if we look at the tracks coming in, the data coming in after the fact, in the later times, they're all falling nicely within plus or minus 3 sigma. So this just looks like we might have a potential bad sensor or a mistag, and this is really not a concern. Let's take a look at another example. Here we can see our residual ratios are looking pretty good. They're within plus or minus 3. But as you get towards the latter half of the graph, what we can start to see is we're starting to see points going outside the lines. And we're seeing a general trend for that on multiple passes, on multiple sensors. And so what this is starting to indicate to me is I have a problem that's not a particular sensor. If it's multiple sensors, it may be, now I would have to have mistags from multiple sensors coming in. This is starting to look more and more like a maneuver. And I can start to dig down into this and start to say, well, this might, turns out I might see just right ascension points or just declination points or certain other kinds of measurements that are starting to fall out, which also is a tip-off of potentially of the type of maneuver that the spacecraft may be doing. So this is a case where we think there potentially is a maneuver going on, and we need to initiate our processing chain to try to dig into that and figure out whether it actually is or not, and start the characterization process. And then we have to decide what is a recovery from a maneuver. So let's say I have identified a maneuver, and I've actually started to model it and reconstruct it, and I'm flying through it. But at what point do you stop that process? So the recovery period is of interest because as I start to process across the maneuver and get data from the other side, my orbit uncertainty starts to collapse. And so the question is, when is my knowledge of that maneuver and knowledge of that orbit after the maneuver good enough that I sort of declare, all right, stop doing the additional magic processing, and we're going to call it a day. Even if this is your own spacecraft that you're doing this on, that's still a very relevant question because you might be concerned about when is my orbit good enough that I can resume mission operations. And so you want to understand what those time delays are and then analyze what your strategies are for minimizing the time to get back into operations. So again, there's no perfect answer, but we'll take a look at some of the options here to identify that. Okay. So the overall process now looks like this. We have to detect. We think something's going on. We have to do some initial characterization with a little bit of data because I can't wait for the perfect amount of data to come in. It's not operationally relevant. If I have to wait 24 hours for all the data to come in, I can't be in a situation where for 24 hours I don't know what's going on. And more importantly, I may not even know where the object is going if it is maneuvering. And if it's maneuvering in a large enough manner, I may no longer have a good enough orbit solution to actually even find it later on in time. That's when, and again, we don't want to lose track custody. So we start doing the initial characterization as soon as we can with the data that we have, with the understanding that it may not be the best answer, but it's the best answer I can get at this time. Then as more data comes in, more observations, more tracks from our sensors, we can start to continue to refine that estimate and improve our knowledge about what's going on with that maneuver. And at some point, we'll declare that we think we've got a good enough answer, that additional data is not going to make a marginal improvement in that answer, and we'll sort of declare victory and say we're done with this maneuver. We've got it figured out, and we're just going to now wait for the next maneuver. There is the potential, of course, that in the middle of this process, a second maneuver may occur. And this is starting to become more and more of a reality as we look at spacecraft with electric thrusters that are doing low thrust, but many large duration but small thrust maneuvers. So this becomes more and more of a challenge, and that helps to also shape what kind of tracking data you might be trying to get in process and how you might be trying to task your sensors. So we use an extended Kalman filter as part of our processing chain, and the fundamental premise behind this is that if you look at this graph here, the middle arrow coming in from the left is essentially what the filter is doing. It's processing tracking data all the way up to time t sub k. And the filter's estimate of the state being indicated by x, at time tk is based on all the information it had to the left. The filter only knows about the data it has seen. And so the state estimate that it has is based on the data that it's seen. But as I continue to process farther down through time, and I can get time t sub l, I have the option now to sort of run backwards in time, and that's what we call our smoother, where I can run backwards in time, and I can go back and look at that same time tk and say, now that I actually have gone past it, but look back, I can refine my state estimate at time tk and take advantage of the information of the tracking data that I have from both the left of tk and the right of tk. And because I have more information, the smoother can make a more accurate or more refined estimate as to what's going on. We're going to take advantage of this because the smoother gives us a smaller covariance, it gives us a better answer, and it allows us to do some really powerful tests, such as what we call the filter smoother consistency test. And this will become very useful in our maneuver processing and diagnostics. The filter smoother consistency test is a test statistic that looks like this. I can take any parameter in my state space, call it x, and I can take the estimate of that parameter from the filters, that's our xf. I can take that same estimate from our smoother, call it xs, and I can difference those two and say, we know they're not going to agree because the smoother had more information than the filter. It has a better answer. But we can say that the difference between those two estimates should have an uncertainty that's described by the term in that denominator. Essentially, it's the uncertainty from the filter subtracted from with the uncertainty from the smoother. You square them, you difference them, you square root them. And essentially what we're creating here is a test statistic that says, are the filter and the smoother solutions and uncertainties consistent with each other? And if they are, that test statistic should be within plus or minus 3. And what we've been able to show is that this consistency test is a necessary condition for having a realistic covariance. This is a really powerful test because it allows us to identify any modeling problems that we have in our scenario. So if I don't have the force model set up right, I don't have the measurement model set up right, I don't have the measurement, the sensors calibrated correctly, it starts to show up in this consistency test, and it's essentially a great canary in the coal mine as to what's going on. And typically we'll apply this test in the position states or the velocity states to identify if things are looking odd, although it can be actually applied to anything in the state space. Okay. So as I mentioned, passing the filter smoother consistency test is a necessary condition for having a realistic covariance. Failing the test indicates that we have somehow lied to the filter. Now there's a variety of different lies that you might use. So for instance, my force model is too simple. If I'm in a LEO orbit and I'm in high drag and everything else, if I use a very simple model for my spacecraft shape, or I don't have enough gravity terms turned on, then it will start to violate my filter smoother consistency test. And that it's a suggestion to me that perhaps I don't have enough fidelity in my models. It's also a common cause is because you've lied to the filter about how good your measurements are. If you have a radar that only has a white noise sigma of 10 meters and you tell the filter that it's a 1 meter accurate radar, what you're going to find is that the filter and the smoother are going to collapse the covariance too far because they think the measurements are too good, and that's not going to hold up when you start running the filter smoother consistency test, and we'll flag that. In the context of this discussion, we're talking about maneuver processing. A common way to fail this test is because you've either not modeled the maneuver at all or you've mismodeled it. And a maneuver really is just another force model that we're using, but we're going to worry about that specifically and talk about how you might model the maneuver, and if you mismodel it, how we detect that. Okay. So let's take a look at an example of a spacecraft that is doing a maneuver. In this case, we're looking at particular residual ratios from measurements that happen to be time difference of arrival measurements, or TDOA. And this is the same residual ratio plot we were looking at before. Notice the scale is much larger. And what we can see is that we've got our editing bounds at plus or minus 3, which are the black lines. We can see that we've got a bunch of different color points, red and blue in there, in the first half of the graph that are coloring within the plus or minus 3 very nicely. So up to that point, our orbit solution is looking very nice. Our residual ratios are well behaved. And then something happens around 0900 or so, and we can start to see that the residual ratios now are significantly larger. They're much outside of our editing criteria of plus or minus 3. And this is a tip-off to us that something is going on with this spacecraft. And they're all out, and they continue to stay out. Okay? So this says that somehow something has happened in roughly around 0900 or so, where we can see we went from good to bad. So this is a typical maneuver type hypothesis when we say we think something's going on here. This happens to be a normal station keeping maneuver. How much your residuals diverge depends on the size of the delta V, the direction of the delta V, and the accuracy of your sensors. Okay. So if we model the maneuver correctly, and we'll talk about how we got there, but let's just hypothesize that we have done it. Either somebody told us or we somehow reverse engineered it. Then what we should see is something that looks like this top graph. What we've done is we actually marked the maneuver with that vertical line there in the middle, and it's actually a finite maneuver, so that line actually has some width to it, although it's difficult to see at this scale. But what we can see is that the residual ratios now are within plus or minus 3 sigma, not only just before the maneuver, but also after the maneuver. This suggests to us that at least from the residual standpoint, we've got the maneuver modeled correctly. But it's also important to look at the consistency test results. So what we've done is we've got in the bottom two graphs, we've plotted the position and the velocity consistency, and we've got three lines on each graph corresponding to the radial in-track and cross-track consistency values. So if you see in the bottom left, we've got our radial in-track and cross-track position consistency, and they're well within the plus or minus 3 criteria that I had discussed earlier. Same thing is happening on the right with the velocity consistency. So essentially I have three indicators here telling me I think I've got my maneuver model really dialed in very nicely, and that it represents what's going on with the actual spacecraft orbit. Okay? Now, let's introduce a modeling problem. Let's say that I think I have a maneuver, I've got my maneuver model in there, but I didn't quite get the time of the maneuver correct. So in this case, we're talking about a GEO, but I've got a 10-minute error on my burn center time. And let's see how that manifests itself now in some of our metrics that we're looking at. So on the top, we've got our residual ratios. Looking good on the left, but on the right-hand side of the maneuver, we've got some of them are okay and some of them are not. So this suggests that maybe things aren't quite right. But maybe it's a bad sensor, or maybe it's a mistag. If I look in the bottom graphs at the consistency test results, you can clearly see that we're going well outside plus or minus 3 as our test metric. And these are really tip-offs to me that I've got some sort of a major modeling problem going on here. And you can see that in the position consistency, it's blowing up. And then in velocity, it's blowing up as well. And as a matter of fact, which axis is blowing up is also indicative of potentially suggestions as the type of modeling error that you may have. So that was pretty obvious. But now let's go to a much smaller modeling error. Now I'm only going to get the burn time off by 30 seconds, which at GEO you might argue is unobservable. And it turns out, as you can see in the top graph with the residual ratios, it really is unobservable in residual ratio space. Those residuals look great both to the left and the right of the maneuver, which would, if you just only looked at residuals, would suggest to you that you've got a great model. Well, you've got a good model, it's just not a great model. And we can tell that, but again, by looking at the consistency test results in the bottom two graphs. We can see that it's not nearly as bad as it was, but we're still violating our plus or minus 3 sigma test. And this suggests that there's still room to improve our model here and try to get this dialed in. So this process used to be something that you can do by hand by going through and changing your model and reevaluating the proper metrics and tweaking things. And if you have a lot of time and you only have 1 or 2 satellites, this is a very reasonable approach to do. Problem is it doesn't scale. Okay? So if you're looking at an SSA problem, you're trying to process an entire catalog, where you have to deal with this all the time, you need to automate the entire processing chain. And that's essentially what we've done. So for context, in a previous year with our ComSpock, as we were processing data, we found just shy of 20,000 maneuvers in 1 year. And so that just doesn't scale to having people on console hitting stuff, doing it by hand. You got to automate the process. So we built our maneuver processing tool. This is an application that essentially attaches to ODTK, which is our orbit estimation tool, takes control of it, and starts automating the analysis of how do I tweak my maneuver models, how do I identify which ones are potential candidates, and start to reconstruct the maneuver so that we can find out what best fits the data. It's a multiple hypothesis formulation. We're evaluating a variety of different options and scoring them as to which ones are sort of the best guesses or the best estimate of what the maneuver is based on the data we have. And then as we continue to get more information in, MPT will refine that maneuver estimate and continue to suggest which hypotheses are still current, which ones should be rejected, and refine the estimate. Okay. So we'll take a look at MPT and how it actually works. And what we can see in this first initial look at it is we've got a variety of hypotheses indicated in the top box. So typically for a nominal GEO, you might be looking at a cross-track hypothesis, an in-track hypothesis, a dual burn in-track, a dual burn cross-track. You can get other additional hypotheses such as a radial cross-track, a dual burn, and you can build your own hypotheses and put them in there. But these are sort of the nominal things that GEOs do. This is not a GEO-specific tool, by the way. This happens to be just the example that we're looking at. This applies equally well to all orbit regimes. As we go through the processing and start refining and looking at the different hypotheses, what you might find is as we go through a first guess part where we come up with an initial guess And we think it was a cross-track burn at a particular time with a particular duration. And this is all done, by the way, with finite maneuvers, not impulsive. And then we've actually come up with an initial score for, or objective function for how well we think this first guess fits the data that we have. What we're trying to do is minimize our objective function to as small a number as we can. We also are looking at the issue of what if the no maneuver hypothesis really is the correct assumption? And as we get more and more data in, you might find that the null maneuver hypothesis is actually the winning answer. Then we'll go through a refinement stage where we try to optimize our first guess and really get it dialed in, and that's what you see in the bottom row there. So let's take a look at how this actually looks in reality. So what we can see here is we have a scenario in ODTK with a geo, a couple of ground trackers, and we're going to generate different reports and graphs to take a look at what's going on. Here's our residual ratios. You can see that we were coloring within the lines, plus or minus 3 sigma, and then something happened, and we zoomed in on that. You can see our residuals are diverging. We're looking at TDOA and FDOA measurements in this case. Clearly something has happened to this particular spacecraft. We're failing our consistency tests. All sorts of bad things are going on. And so this is indicative of a potential maneuver that we want to investigate. So what we're going to do is we're going to start up our maneuver processing tool. It's going to essentially attach to ODTK. And we've given it a list of hypotheses to investigate. So cross-track, in-track, the dual burn scenarios. And the first thing we're going to do is run what we call a residuals versus reference step to just get some baseline data on what does this maneuver potentially look like, and how does the data fit the null maneuver hypothesis. Now we're going through and scanning through each of the proposed hypotheses to take a look at how well they fit the data. And so we're going through the initial scan process here, and you can either look at the top level view, or you can actually monitor the log file, which is what we just saw, where we're giving you a blow-by-blow analysis of what step we're on and what's happening. So it's going through and analyzing the cross-track hypotheses, and essentially it's postulating where the maneuver might be, how big it might be, and seeing how well that fits the data. While this is running, we're actually taking advantage of the fact that we have multiple cores, and we can actually we're spawning multiple copies of ODTK in the background, because many of these steps can be run in parallel. And we'll take advantage of the fact that we have multiple cores, and this is all processing as fast as we can to figure out what our options are. All right, and so what we found is that we think we already have a first guess from our cross-track solution. And these are actually ordered based on their likelihood of fitting. So we analyzed the cross-track. We actually found a good enough first guess that we're not even going to evaluate the other hypotheses. This speeds up the entire processing time. And what we see now is we're actually now taking that first guess, and we're rolling into a optimization process now, where we're actually running an optimization routine. And what we're doing is we're tweaking the start time of the maneuver. We're adjusting the burn duration and trying to get that really dialed in. And we're monitoring the objective function, which you can see happening in the lower right where the mouse is. And our objective function right now is 4.9, which is a really great fit because our null hypothesis, the no maneuver hypothesis, was well up into the 800s, which is essentially what you're seeing when you look at those consistency tests and residual ratios that we had originally from the no maneuver run. So we've got a good answer here. The optimization process is done, and we've got a nice low objective function. So what we can do at that point is accept that solution. All right, so what we've done now is we've actually solved for our best solution possible. And what we're going to do now is bring that back into, we've brought it back into ODTK, and we want to generate some output products to show how well that fits. So we'll take a look at our residual ratios. We're going to do that in both TDOA and FDOA. We can see our TDOA residuals look great. They're plus or minus 3 sigma. We can see the finite maneuver that we solved for. We're going to do the same thing with the other measurements. The FDOA also looks great. So we really like this maneuver so far, and things are looking good. And we'll take a look at our consistency test, and we'll look at the size of the maneuver. So in this case, the maneuver was cross-track. We can see the thrust level, fairly constant thrust, so we like that. It doesn't have to be that way, but we can see if it was changing. We'll take a look at our orbit uncertainty. This is the uncertainty off the filter, and we can see that that maneuver increases our uncertainty, but then it will come back down as we continue to process measurements in there. Take a look at our velocity uncertainty. Again, as you might imagine, the velocity uncertainty increases during the maneuver, and then it collapses again post-maneuver. And we're getting down to our pre-maneuver uncertainties. Now, if you look at the smoother uncertainties, we can see that they are much more accurate, and we don't see the increase because essentially as we've processed across the maneuver, and we've seen that the smoother has gone backwards across it and folded the information back. So we have a very good understanding of what our orbit accuracies were across this maneuver. We'll take a look at our consistency test. And again, in position and velocity, we can see that the consistency test is within plus or minus 3 sigma. So this is all, again, consistent with the fact that we think we have a good maneuver model as found by the maneuver processing tool. Okay. So what happens is when you apply this at scale and start running this in an automated sense, and again, this is what we do in the ComSpoc with our SSA suite, you can get results that look like this, and this is a sample dump from our SSA suite. And we can see each of the maneuver IDs, the space object that it was on, the maneuver burn center time, the duration, the scoring metrics, how well we think we actually fit this maneuver. That's what our quality metric column is there. And then the size of the delta V, what direction it was in. And again, you can dig into each of these and get more details. But this is a nice summary that you can start to pull down and look at and get the information on each of the objects in question. This type of a display, we're running at this at scale with hundreds and thousands of objects. That's part of our SSA suite. With the maneuver processing, it's the exact same tool and the exact same process. So what we've learned now is that there are ways to go through this and address this problem. We've got the capability to do that. We don't make any simplifying assumptions at all, so we can do finite maneuvers. We can do it with any measurement type, not just ground range and angles or RA deck. We can use more advanced measurements. And while we have general hypotheses about typical directions like in-track and cross-track and things like that, there are actually capabilities in there to do maneuvers in any direction. And so it's possible to reverse engineer in the blind, maneuvers as large as kilometers per second and successfully do that. So we think this technology really gives us a nice advantage, and it gives our customers the ability to handle situations they previously couldn't and really focus on now not the mechanics of solving for maneuvers, but now they get to focus on the problem of what do I do with this information and take advantage of it. Thank you very much.